times 10 to the power 3 pounds, and it's going to be tensile. Okay, that's what we know. So any question for section 1? Everyone okay? Right.
Just sir, again, what's P1?
P1 is the load applying on section 1. Okay, so this is, so basically this is your P1. Okay.
All right. Yeah.
Okay, so it is addition of everything. Okay, so the next one we are going to look into section number 2. Okay, so I'm going to string this. We're going to look at section number 2. So for section number 2, we have this geometry over here. All right. So this is our section number 2. And for section number 2, right, we are going to see a compression of 45. Okay, let me redo this. We see over here 45 times 10 to the power 3 pounds, and then we are going to see the 30 times 10 to the power 3 pounds. Okay, so over here this is point B and this is point C. So section 2, P2, so we now know that 45 will still induce a compression, and then 30 is going to induce a tensile. Okay, so what we have is P2 is equal to minus 45 times 10 to the power 3 plus by 30 times 10 to the power 3. So this will give us a P2 of minus 15 times 10 to the power 3 pounds of force, and minus means compression. Anyone, any question? I hear someone unmuting, thinking now. Mr. Paris, no?
I'll ask a question for the class. Why don't we use a 75?
Yeah, where are you? Who is that?
Brayson.
Yep. What happened to the 75? I was just waiting for that. Okay, what happened to the 75? Good question. So we know that we have a load down here, right, of 75 times 10 to the power 3 pounds. And we did not include that, right? So is there any tricks? And the answer, there's no tricks. So let me explain this. Okay, so I'm going to take the structure. Okay, I'm going to take the structure. I'm going to take this structure over here. I'm going to paste, and then I'm going to rotate. Right. Okay. So whether the structure is horizontal or vertical is the same. Okay. Right. Now, if we look at the structure in a vertical or in this way, okay. So when you solve this problem, it's good to draw this. It is good to orientate your figures in this direction. Now, section 1 will see the 75, will see the 45, and will feel the what? It will feel the 30. Okay. Section 2 will only feel the 45 and will only feel the 30. Okay. Now you will ask me, Eugene, you are just speaking louder now. I still don't understand. Am I right? Yes or no? Come on, someone just reply.
You're right.
I like that. Okay, I like that. Right. Yeah, he's just saying in a different way. He just oriented the diagram and okay, let's look at the hanging man philosophy. Right? Let's look at a hanging man philosophy. So we have a man that's going to be hanged. And over here is his head. I'm not being funny down here, okay? I'm just drawing. And then this is his upper torso, right? There is his upper torso. And then these are his legs. Okay. Right. Then I'm going to divide this into upper body. So this is your upper body. And then we're going to divide this into our lower body. Bear with me, okay? And then we are going to have our hips and legs. Okay. Right. Your upper body, right? So if we were to focus on our upper body now, our upper body, what can they feel? Right? When they're going to be hanged. So let's say if this is or yeah, if you were to hang the person's neck, okay, we're going to hang the neck, right? What can the upper body feel? Anyone? What weight can the upper body feel? Anyone?
Tension.
Yeah. It can feel the lower body and the what?
The hips
And the
and
hips.
legs.
Hips and legs, right? Right? So if I were to cross this section over here, what can it feel? Where I draw a circle, can it feel the lower body weight, upper body weight, or it can only feel the hips and legs?
Hips and legs.
Yeah.
Hips and
It can only feel the hips and legs. So exactly where this come in. Okay. In section 1, it can feel, so in section 1, right? In section 1, it can feel the 75, 45, and 30. In section 2, it can only feel the what? The 45 and the what?
30.
And the 30. And then lastly, this part over here, it can only feel the what?
30. The 30.
30. Right? Does that make sense? Yes or no?
Yeah, it makes sense.
Yes.
Right? So if you have this sort of problem, what I always do is I always orientate it vertically, and then it's so much clearer. I know looking at it horizontally, like it takes me a while. Okay, if I do it vertically and do the hangman philosophy, it is so obvious. Yes or no? Okay. I do apologize. Okay, can you hear my background?
No.
No? Okay, because my daughter is screaming. She's making fun of me now, okay? Yeah, she's unbelievable.
I can
It's
hear
okay.
them.
We're in the same boat.
Yeah, okay. We're on the same boat. You mean the bloody sinking ship, right?
If you want to look at it that way.
Okay. So we're going to look at section 3 now. Okay, section 3. Right, so section 3, like what we have spoken earlier. Right, so this is section 3. And then section 3, it could only feel, okay, it could only feel the 30 times 10 to the power 3 pounds. And this is also in tension. Or tensile. Okay, let's standardify. If I call it tensile, make it tensile.
Should we erase the 75 from the previous block?
No, leave it there. Okay. So as long you know why I did not, in fact, you want I can put all of them in. Okay, so it's okay, just leave it there, but you know that you don't need to consider it. I think that's more important
Okay.
than anything else. Okay, so finally we have P3, and P3 is 30. So sorry, it's positive 30 times 10 to the power 3 pounds, and this is in tensile. Okay, so a student just now asked, why should we section it based on the forces? Okay, can you see now why? Okay, so based on the forces, I've sectioned it based on forces. Then we can analyze, because some of the forces at some section it don't take up the load at all. Okay, so that's why you divide based on the forces first. Okay, then you divide based on the different material cross-sectional area. You use the largest number of division. Okay, right. So from here we know that A to B we have tensile, B to C is compression, and finally from C to D, right, it's under tensile. Okay, so the philosophy down here is we're going to use the hangman. So from here we know that we're going to calculate the total deflection. Right, we're going to calculate the total deflection. So this is equal to P1 L1 over A1 E1, then plus, for now just do the plus. Okay, so plus by P2 L2 divided by A2 E2, then plus by P3 L3 divided by A3 E3. So for this question, okay, is made of one material. Okay, so make of a single steel material, right? So it's made of one material, so the Young's model is always the same. The only thing that changes is the cross-sectional area. A to B, the area. Hey, why the area gone missing? My bad. I do apologize. So down here, the area is equal to 0.9. Yep. Inches squared. Okay. So A to B has an area of 0.9 inch squared and the length of 12 inch. B to C is the same. C to D is 0.3 and 16 inch. Okay, then you just, now it's just matter of putting the so P1 is equal to, I think it's positive 60 plus by 60 multiplied by 12 divided by 0.9, and Steele's Young's modulus is 29 times 10 to the power 3. And then at section number 2 is minus. Why minus? Because it's going for compression. So minus 15 times 10 to the power 3. I made a mistake earlier. Is 60 times 10 to the power 3, not just 60. And the length is 12. Likewise, multiply by 12. Now divide by 0.9. And then it's 29 times 10 to the power 3. And the last one is in tension. And then the length is 16. I think the cross-sectional area is 0.3. And this is 29 times 10 to the power 3. Okay. So once you add up everything, your total deflection is plus 75.861 times 10 to the power minus 3 inches. Okay. So what does the positive means? The positive means that this structure will extend, the deflection total will go towards the right. Okay. So for this example, right? So it's not difficult at all. It's pretty straightforward. The only difficulty is what section consider what load. Okay, and that's based on the hangman. So to summarize on this example, is the first thing we'll do, you divide